In my class 12th, one day my teacher came into class and took a topic, electric dipole, and she taught everything about the dipoles, in which she thought that it's basically two equal opposite charges with kept at a distance d apart. And she taught about its field nature, how it field looked like, and she taught about it experience a torque when we place it in an electrical field, and it has an electrical field and it has a potential. So the class ends. I just thought about that. Why should I learn about this dipole? And what property this dipole have in which the other charge systems doesn't have? What this dipole have some peculiarities? Let's look at the charge system. Yeah, in these systems we have a 5 coulomb positive charge and minus 2 coulomb negative charge that is separated by a distance d. And if you try to find out the electric field at the point P, then we can just add simply the electric field to the plus 5 q charge and the minus 2 q charge. That is K5 divided by R1 minus K2 divided by R2. This formula we can be used, but if the value of the R1 and R2 is very close, very far, very bigger than the distance d, we can just approximate this formula as R1 is equal to R2 is equal to R. Then we got the electric field is equal to 3k divided by R. And this formula is only valid if there is any net charge in that place. If there is no net charge, then the electric field will be equal to 0. But that does not be happen. And if you look into this equation, we can see that it is actually the electric field due to the net charge in that position. Yes, if you place a 3 coulomb charge at the origin and if you take a point very farther away from this point, if r is very greater than the dimension of the thing we're taking, then we got the same electric field as in this case and that case. If we have a dipole, in this case, how would we find the electric field at a further point r, where r is very greater than as compared to d? We cannot approximate as in the previous case because if we approximate the r is equal to r1 and r2, then the electric field will be equal to 0. So what should we do? In this case, we can use the electric field to a dipole at that point. It is an approximate formula also, but this formula is approximated using some binomial expansions. And we can use that formula to finding the electric field at that point without knowing any net charges. What would, if we have systems like this, like if the net charge is 0, but have some dipole moment, because the charges get shifted from their original position due to some thermal motions, etc. I don't know any information about why does it, but it is just separated. So how can we calculate the electric field at a further point? If we know only about dipole moment, we can actually calculate. Let's see how. Let's suppose this system contains dipole with the dipole moments P1, P2, P3, P dot 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 Pn, etc. And each constitute an electric field at the point P. That's why we can add all this electric field to each dipole, like E due to P1 plus E due to P2 plus E due to P3 dot 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 E due to Pn. We can add. That's why we got the electric field at that point using the dipole equations. It's very powerful, right? Then I know there's a question arises in your mind that what if the net dipole moment is 0? Like the net charge is 0, and if the net dipole moment is 0, in such systems what will we do? Let me show a system like that. Yeah, in the system, how can we find the electric field at the farther point? If you try to approximate using the dipole electrical field, then it should be 0. And if you find the net charge, if you try to find the net charge, then the net charge should be equal to 0. Then what will we do? In this case, we have some other terms like quadrupole and octopole, etc. These such terms will be used to find the electric field at that point, like the same way as in the dipole case. The dipole which has a dipole moment, this quadrupole terms has a quadrupole moment. And again, I am saying that this all comes if try to approximate the electrical field. If we calculate the electric field using k q1 divided by r1 plus k q divided by r2 plus dot 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 k q and divided by rn, then there is no need of any of these quadrupole, dipole, and monopole, any terms. But if we try to approximate the electrical field, then we have to use this little charge like moment, quadrupole moment, etc. etc.